So this is a recording about buffers, and buffers are really an application of a common ion system. Now, a buffer is really an aqueous solution that contains a mixture of two things. It's either a weak acid and its conjugate base, or a weak base and its conjugate acid. And I just gave you a couple of examples. This is a really common weak acid, which is acetic acid, and its conjugate base, the acetate ion. And then we have a base below it, which is ammonia, and its conjugate acid, the ammonium ion. And the idea with a buffer system is that you have high concentrations of the weak acid or weak base and its conjugate, and when you add an acid or a base, small amounts of it, it resists changing its pH because the equilibrium will shift when you add that. Okay. They're very useful because they keep a constant pH value, and a lot of biological systems need to maintain a constant pH. A common buffer system that you see is actually our blood, and it's useful because our pH of our blood doesn't change if you were to eat something very acidic. So like if you had a lot of salad dressing, that wouldn't change the pH of your blood, which is what we want. Now, there are 7 strong acids, HCl, H2SO4, HClO4, HClO3, HI, HBr, HNO3, and each of these is considered strong because for every molecule it gives at least one hydrogen ion. Now, I put a star next to the sulfuric acid because it's only strong for its first ionization. So it's only going to remove the first hydrogen ion, and that one's strong. The HSO4 that's left behind is actually still an acid, but it's weak. And so it doesn't dissociate into SO4 2 minus, it dissociates into HSO4 minus. Almost every other acid you can just consider to be a weak acid. And if you're given a Ka value, that implies that the acid is weak. Alright, so let's try a problem that involves a buffer system. So we have a buffer here that is formic acid, HCOOH, and formic acid is the venom that comes from ants. And in this system, we also have sodium formate, NaCOOH, and in both of these, you find the COOH minus ion, and that's the common ion that they have. Remember, buffer systems are just applications of a common ion problem. Now, I was kind here, and I already calculated the molar mass that we're going to need, and the Ka value, I looked that up, and at 25 degrees, it's 1.7 times 10 to the negative 4. Alright, so the first thing you're going to do when you solve this problem is start out by finding your molarity. So I just took the mass, divided it by the volume, and that gave us the solubility in grams per liter. And then I took the molar mass and converted it into molarity, moles per liter. Now this is the molarity of the sodium formate. And we know that when this dissociates, since sodium is group 1, then it's going to dissociate completely into the sodium ion and the formate ion. And they're all in a nice 1:1:1 ratio, so their molarities are equivalent. Alright, so now that we know the molarity of the formate ion, I just carried that over from the previous page, and we know the concentration of the formic acid, we can now set up an ice diagram that allows us to figure out what the concentration of hydrogen will be at equilibrium. So I filled in the values we know. We can assume that we are starting with 0 of the hydrogen. And so because we know that that's 0, we know that the products have to increase and the reactants have to decrease. And we don't know how much, so it's going to be X, and our ratio is 1:1:1. So that makes that nice and easy. So I'm going to fill this in, 0.14 minus X, X, and 0.18 plus X. Now that we have these equilibrium values, we can plug this into our next expression. Okay, so we knew that the Ka for this was equal to the concentration of the hydrogen ion, that was X, times the concentration of our formate ion, all over the undissociated hydrogen formate or formic acid. Now I've just rearranged this and subtracted my constant to set it equal to 0. I plugged it into my solver button and I set my boundaries from 0 to 0.14. Now I chose 0.14 because I looked at the parenthesis that had the negative in it, the subtraction, and solved for the maximum value that X could be. So X could be a maximum of 0.14, so that determined my boundary. And when I plugged this in, my calculator said that the value for the X, which is our hydrogen ion concentration, is 1.34 times 10 to the negative 4. So this is the concentration of the hydrogen at equilibrium. Now, that wasn't all that this problem was asking. The problem actually asked for the pH of this. So now that we know the concentration of the hydrogen ion, we want to find the pH. Now, we know that pH is defined as the negative log of the concentration of the hydrogen ion. So all I'm going to do at this point is solve for my pH by taking the negative log of 1.32 times 10 to the negative 4. And the pH is 3.88. And that solves this problem.